Given that strict consistency is next to impossible to achieve, the next best option with reasonable cost is sequential consistency. If we look at the example from the previous video, if x and y are completely unrelated, and P2 computed the value of y independently without any reference to the memory location M1, then these two operations don't really have to strictly appear in this particular order. For instance, it is possible for P3 to observe, just like what it did in the previous case, that the value of M1 has become x, and then to see that the value of M2 has become y. But it is also perfectly reasonable for P3 at a particular point in time to access the value of M1 and to see that it's still 0. So it doesn't know that this write operation happened. However, at a subsequent moment, when it tries to read the memory location M2, it sees that it has already been updated to y. This is the equivalent of what would happen in a regular shared memory system if we have multiple threads and if we don't use any additional controls, any locking, synchronization, anything like that. When these two operations are issued, they will be applied in some way, some order, but we don't necessarily have control which is the order that these operations will be applied in. So that's why we say that as long as the ordering that's observed is equivalent to some possible ordering of these operations if they executed on a single shared memory system, then that will be considered a legal operation according to this sequential consistency model. So in summary, according to sequential consistency, the memory updates from different processors may be arbitrarily interleaved. However, if we let one process see one ordering of these updates, we have to make sure that all other processes see the exact same ordering of those updates. For instance, it is not okay to let process P3 see that the update to M1 with the value x appeared before the update of M2 with the value y, and instead at the same time to allow process 4 to think that the value of M1 was still 0 when the value of M2 was already updated to y. In this case, process P4 thinks that M2 has been updated before the memory location M1. It would be too hard to reason about what exactly will happen in a program execution if every processor can see completely different ordering of some updates, and if the software or the programmer doesn't have an understanding how and when are those updates reordered. What this means is that with sequential consistency, every single process will see the exact same interleaving. This interleaving may not correspond to the real way in which these operations were ordered. However, sequential consistency at least guarantees that every single process in the system will see the exact same sequential ordering of all updates. And one constraint of the interleaving is that the updates that are made by the same process will not be arbitrarily interleaved. For instance, if P1 makes another update in the future, then on any of the other processes, it will not be possible to first observe that the value z was written to the memory location M3, and only then find out that the value x was written to memory location M1. So for instance, what we see on P4, this will be correct under sequential consistency because the updates to M1 and M3 are observed here in the correct way. When it sees that the value of M3 was z, it already knew that the value of M1 had become x.